Okay, good morning everyone. I'm Andrea Benericetti and I work as a data scientist at Verizon Connect here in Florence. Today in this presentation I'm going to talk about some of the approaches in the machine learning fields that we adopted to tackle the task of road scene video analysis. Now, first of all, I'd like to give you a brief introduction of who we are as Verizon Connect in order to let you understand why we had to deal with such a task and why we had to solve it. So, as you may guess, Verizon Connect is a US-based company under the wing of Verizon, which is one of the biggest, telecommunication companies in the world. Actually, we don't have anything to do with telecommunications because our core business is the vehicle tracking. So our efforts are towards an ongoing connection of each vehicle on the road in order to make them connected, to be able to know every time where they are, and so on. Our core business is actually divided into two main branches. The customers one, where we help our single customers deal with safety, consumption monitoring, navigation, and so on. An example of one of the products that we developed for the customer business branch is HUM. Then the other branch is the enterprise one, where our customers are fleet owners, such as delivery companies, logistic companies, and so on. In this case, our purpose is to help them in managing and monitoring their fleet. For example, letting them know in real time where each of their vehicles is, if there was any harsh event, and so on. Verizon Connect, despite being based in the US, has actually quite a lot of offices all around the world. We've got offices in Spain, in Portugal, in Ireland, in India, in New Zealand, and two offices here in Italy. One based in Ferrara, and the other one here in Florence, a couple of kilometers far from here. Our Florence team is comprised of two main teams. The web development. No, those guys. and then the data science one. Okay. I'm part of the data science team, and as such, we are deemed in adding a semantic and artificial intelligence layer to all of our products in order to make them able to automatically be able to detect some kind of event, and so on. Currently, we have ongoing collaborations with the University of Florence and the University of Bologna. Now, the basic building block of all of our systems so far is the vehicle tracking unit. It is a small device containing a lot of heterogeneous sensors, such as GPS, odometer, acceleration, consumption monitors, and so on. These devices are installed on each vehicle, usually plugged into the ODB2 port of the vehicle or directly to the battery. And they work sending a message at about 10 seconds, a period of 10 seconds, sending the current state of the vehicle, such as its position, its acceleration, its direction of movement, and so on. In addition, the VTU is able to trigger the so-called harsh driving events based on simple thresholds over the acceleration, which means if there is a strong brake, the acceleration goes over a certain threshold and the VTU sends a message. Now, with all the data that we've gathered throughout the years of VTU messages, we have developed a lot of smart products, such as stop purpose classification, which means identifying the stops of the vehicles and detecting their purpose. Hotspot detection, which means identifying which stops are actually hotspots, for example, the depot of the vehicle or the driver's zone, and so on. The vehicle itself classification, which means understanding from the messages which kind of vehicle is mounted on, a car, a truck, a bus, and so on. And one of our latest works is the VTU Health automatic detection, which means taking a look at the pattern of messages sent lately and detect if there is some kind of problems or fault on the VTU itself. Now, our long-term goal is to go towards a complete understanding of the scene surrounding a vehicle. Obviously, we cannot just rely on the messages sent by the VTU, but we need to have some source of information. Nowadays, one of the most well-known sources of information around us are video. We are accustomed to have cameras in our smartphones, in our laptops, around the streets with surveillance purposes, and even sometimes on cars with the so-called dash cams. A dash cam is a camera mounted on the dashboard of the vehicle, just its name suggests, usually recording the front of the vehicle. Then sometimes we have other additional cameras recording its back, its sides, and sometimes even the inside of the vehicle. Obviously, adding video to our datasets might mean adding an enormous source of information. Most of this information is actually noisy. Just to give you a couple of examples, these are two videos taken from YouTube. This is a video of an almost crash. Almost. This, as you can see from the thumbnail, it's going to be a crash. Sorry for the spoiler. This was a crash. Yeah. Now, the first example is actually more interesting than the second one because just looking at the two messages, we wouldn't have been able to detect the risk. We only knew that there was a hard braking, but without knowing what actually caused that. So in this case, adding the video might be useful. No? Okay. Obviously, I did change the tone. Okay. Now, obviously, being a business company, we need to motivate not only the research purposes behind our research, but also the business value. In this case, we are quite lucky because it turns out that our customers want even more visibility over anything that happens to their vehicles and their drivers. So the safety is quite a strong purpose. In these cases, for example, our customers might like to use the video for insurance liability, driver coaching, rewarding of positive behaviors, and theft detection. Adding a video could mean opening a whole set of doors towards a set of different semantic layers. For example, on the lowest level, we might want to be able to detect the event severity. We might want to be able to detect if there is a short following distance, so if we are too close to the front vehicle, or kinds of violations such as the overspeeding and traffic light violations, up to higher level motivations such as detecting the involved subjects in a crash, in an event, and the event type itself. Now, ideally, the best use case would be when we are able to perform such detections in real time on the recording device itself, the camera. This is quite feasible for easier problems, such as sign recognition or traffic light recognition or short following distance detection. But when we go to more sophisticated semantics, such as the event severity or the detection of involved subjects, the current hardware is actually not cheap enough or not powerful enough. In this case, we need to go to a two-phases process. First of all, we need some kind of chip detection on the device in order to detect the actual events. For example, we might want to take a look at the G sensor, the accelerometer, and then rely on heavier, stronger video processing in the cloud on a server in order to refine this classification. Now, I'd like to move to one specific project, the so-called Ludovico project, that we actually developed in order to deal with the problem of event severity classification. As I said before, our VTU are able to detect some of these events based on the accelerometer. We've got harsh braking when the vehicle brakes too much, quick acceleration when the acceleration goes towards the direction of movement, and cornering when the acceleration is longitudinal to the direction of movement. Now, the problem is that when we've got a big fleet of vehicles, and our customers have thousands of vehicles, this fleet can generate hundreds of events in a day, but obviously they're not going to be all equally important. So the idea was to add the video in order to extract information from the video and to be able to identify the more dangerous one, the most dangerous ones, and give a ranking of severity in order to reduce the number of notifications and letting the customer take a look only at the really dangerous ones. Just a fun fact, the name Ludovico, as the GIF suggests, comes from the Clockwork Orange movie, because when the project started, I wasn't in the company at the time, my colleagues say that spent a lot of time taking a look at videos of crashes and near crashes on YouTube, and they say that their feelings were the same as Alex, the main character of the movie, when he's forced to undergo the Ludovico technique, which is being forced to look at violent videos while listening to Ludwig van Beethoven, Ludovico in German, music. Now, the baseline, the high-level baseline of the project is to wait for an event, for an harsh driving event, and then collect the telemetry profile from the VTU and the video from the cam, and then combine these sources of information in order to classify the event as one of 4 classes: crash, high risk, mid risk, and low risk. We've got a crash when there is a collision, any kind of collision with any entity with the vehicle. We have high risk when the driver is forced to perform an evasive maneuver in order to avoid the collision. A mid-risk when this maneuver is present but there is no immediate risk of collision. And then we've got the low-risk ones when there is little to no risk. Now, this problem is that these definitions are quite fuzzy and substantially overlap. So we have a lot of borderline cases when the event is actually difficult to classify. In addition, we've got the problem that this dataset is highly unbalanced because high-risk events, that are the ones that we want to focus on, are actually rare. So we're going to have a lot of low-risk events and only a few crashes and high-risk ones. Now, this problem is substantially similar to the action recognition in videos. This is not yet a solved problem. Actually, it should be a solved problem, but cannot be used in production-ready environments because of 2 main issues. They, being based on deep learning techniques, combination of LSTM, convolutional neural networks, and so on, they are quite slow and difficult to train, or at least they are too slow to be usable in a production environment. And then they are usually trained on and focused on easy and not production-ready datasets. Production datasets are usually really noisy. So our business case is to have, as I said, fuzzy definitions and rare events. And we have to deal with some additional requirements posed from the business branch of the company. This system must be accurate. At the same time, it must be fast and affordable because it's going to run thousands of times every day. This necessity to have a trade-off is going to play a role in some of the choices that we made, and I'm going to describe later. In addition, we can use the IMU, which is the telemetry acceleration and so on data. IMU stands for inertial measurement units, along with the video. So our approach was to start with a combination of computer vision, machine learning, and deep learning approaches in order to build a classification engine. At the same time, build a growing dataset of relevant events, which is really slowly growing actually. And then, as soon as this dataset reaches a critical mass, move to more complex approaches. We are not in that phase yet. So the scheme, the high-level scheme of the system is this one. We start with the video and the telemetry data. We have some kind of preprocessing over the video, another kind of preprocessing for the telematics, then combine all of this in a feature extraction process and feed all the features to a machine learning classifier. Now, for the video, the first block of the pipeline is the object detection. Object detection is the problem of detecting and classifying entities in an image, or in this case, in a video. We chose to use, okay, let me go to the next slide because I'm going to talk with a background, if it's going to start. Okay. This is a YOLO application in real time. YOLO is one of the algorithms that performs object detection. As you can see, it automatically detects entities in the image and associates a label with them. We chose this algorithm because it's a good trade-off between speed and accuracy. Now, as you can see, there are a lot of labels that are actually not useful in a road scene scenario. This is not the case, actually. So we had to perform a so-called fine-tuning. So we took a pre-trained model, which is the darknet implementation, I guess, and fine-tuned it in order to let it recognize only road-relevant elements, cars, trucks, and so on. In our implementation, we chose to use an already implemented network and to fine-tune it, adapting it in order to wrap it in a Python environment, and in order to be able to call it directly from a Python environment. Okay, let me stop this thing, which is going to last quite long. Okay. Then the other phase, once we have the bounding boxes for each entity in the video, it's going to perform a multiple object tracking, which is identifying objects and matching them across the frames. This is quite a challenging problem. It has a large body of research. In our case, we chose, as I said, to use a fast algorithm, which is quite accurate, but probably there are out there more accurate ones. Our idea was to use a maximum bipartite matching between the bounding boxes into consecutive frames. The low-level idea is to have all the objects for a frame, all the objects for the other frame, and find the best matchings between the two frames, where best match is the one that overlaps the most. In this case, we implemented it in vanilla NumPy. Another preprocessing step for the video was to apply dense optical flow in the far-back implementation in order to detect the apparent motion of each pixel between consecutive frames. This is done for a twofold. Okay, no? Okay, I'll stay here. For a twofold purpose, because we want, first of all, to estimate the direction of the ego vehicle, the vehicle which the camera is mounted on, in order to detect its potential collision area, which is this triangle, this blue triangle. Then we wanted to compute features about the motion in each area of the frame. The idea is that if you have a strong motion, you're probably going to have one such evasive maneuver that I described before. In our implementation, we chose to use the far-back algorithm using OpenCV for Python. Then we can combine the object detection and the optical flow in order to realize a real road scene pipeline in which we, first of all, perform a front-rear detection, which means being able to detect the front of the rear of the vehicles, estimate depth and time to contact of each object, in order to be able to detect which are the really dangerous objects in the scene, then estimate the trajectories, these arrows, and then find which of the objects have trajectories that are going to bump into the ego vehicle. These are the dangers for the vehicle. Once again, we realized an implementation using NumPy, SciPy, and Pandas. As for the telemetry features, we had to perform an obvious preprocessing because real data are very noisy, in particular when having to deal with trucks which have a lot of vibrations. We noticed that the accelerometer went mad, so we had to perform smoothing and so on. And we extracted quite simple statistical features from the accelerations: max, mean, median, frequency statistics, and so on. As you can see from this image, this is a crash, and the signature of the acceleration is quite discriminative. So it's a good idea to add this data into the classifier. To the matter of telemetry, we have an important thing to note. We have to make sure that the sensor is well calibrated, because if the calibration is not well performed, we're going to have more noise than actual information, which in sometimes might turn to be even harmful when going on with the classifier. So once having extracted the features from the video and from the telemetry, we can feed it to a classification model. In our case, we chose to use a simple random forest model. This is because random forests are effective, versatile, they are extremely fast. Once again, speed is quite an important aspect of the system. And it has the feature to be able to be adapted to imbalanced datasets through class weighting. This means that in this case, we can use it with some tricks and magic in order to deal with our unbalanced dataset. Once we'll have a much larger corpus of videos and events, we might switch to more complex classification models, such as LSTM, CNN, attention models, in order to be able to fully exploit the temporal component of the video. As I said, we need a massive amount of data because there's a great risk of overfitting. Now, at the same time of building the model itself, we have a side task which is quite fundamental, which is build our own dataset. The idea is that we need to make the training, the test, and the new data as homogeneous as possible. Because, for example, using a dataset to train the model and then another one to use it in real life might introduce sources of bias. Then we would be able to tailor data as we need in order to not to rely on external sources and to choose the labels we want. And last but not least, this dataset might and will be reusable and reused for future works. The process of building a dataset usually requires a two-phase process. First of all, we review and relabel every classification as soon as we receive it, confirming it if it's a good one, and relabeling, changing its classification when it's a wrong one, rare cases, luckily. And then we can add additional metadata, such as the weather, road type, all of these labels that might turn to be useful in later works. The tool of our choice for creating a dataset is Amazon SageMaker Ground Truth, which is a relatively young tool with some good characteristics. For example, it is able to work with predefined types of labeling jobs and custom ones. We chose to use a custom labeling job for our purposes. It supports quite seamlessly multi-worker labeling. So if you want more than one reviewer to agree on the label before adding it to the dataset, you can do it without problems. And then it is integrated seamlessly into the AWS stack, which usually, and in this case too, is quite a good feature. One big con to this tool is the fact that, as I said, it's still very young. It was launched at the end of 2018, and this means that the documentation is rather poor, and the community is quite scarce. So don't hope to find solutions on Stack Overflow, because there isn't. I know. And it still needs, and it's still undergoing with some tweaks here and there. So, going towards the conclusion, this is the technology stack that we used. Under the software aspect, we used, as I said, Python with the aid of some libraries such as OpenCV, NumPy, Pandas, SciPy, scikit-learn, and the YOLO library. Then, for the infrastructure aspect, we chose to use the most common one, Docker, along with AWS and its most common tools, S3, ECS, SQS, SNS, and so on. As monitoring tools, we chose to use Elasticsearch and Kibana. And then, as under the dataset building aspect, we chose to use Amazon SageMaker, in particular in his ground truth tool. Now, obviously, as I mentioned, the severity of an event is just one of the things we can extract from a video. If we start from the same building blocks, it is quite straightforward to add specialized classifiers, train them, and add them to the pipeline. For example, we might want to be able to extract additional semantics on the subjects, or perhaps the cause and the dynamics of the event. And this would give quite a good business values to our customers. Okay. Now my presentation is finished. Thank you. Thank you.
So, if you have some question for Andrea.
So just one question. Working?
Yep.
Okay. As far as you know, from what you said, this process is offline. I mean, it's not online, so it's not aimed to forecast and prevent accidents and so on.
No, it's not preventing. It's a soft real time in the idea that the notification goes to the server, and the server processes it. So it's going to be a matter of minutes, but not from the prevention side, but the notification side. Our customer will know in a few minutes what is happening to their vehicles.
Okay, thanks.
Thank you.
Okay.
So you're saying that you divided your videos in 4 classes of risk.
Yeah.
How are you actually assigning labels to these videos? I mean, is it subjective for the annotator, or?
As I said, it shouldn't be subjective, but actually in some cases it is, because the labels are quite fuzzy. There is some borderline cases in which we have a break which is quite close, but not that much. So we have to review it, to review videos quite a few times actually. And we are trying to stick to the definitions that we saw before, but sometimes we have to argue and make some tweaks here and there to the definitions to be able to find the most divided ones, let's say.
Okay, thanks.
Thank you.
Hi.
Hi.
Question. Did you try also using some image augmentation techniques in order to increase the data set?
Sorry, image annotation?
Yeah, some techniques regarding image augmentation in order to increase the
augmentation.
data set.
Actually, not, because we are trying to think something about this. For example, cutting a video in different points, but we are not using it in a production environment. It might be a source of information, but right now we are receiving quite a lot of videos, so there is not that need of augmenting it.
Okay. Also, another question. I guess that the
the dash cam, the input, is not always the same for each vehicle on which you're mounting the camera. So I'm wondering whether does it influence the quality of the data set? I mean, does the height of the camera make some sort of give some sort of problem, and does it require some sort of normalization being used for input for classification?
First of all, the fact that we mount them as a company is already a help, because the mounters know where to put the dashcam. Then, we have seen some different ways of mounting the camera. But the vanishing point, the cone collision of the car, which is detected during the processing, is already a normalization process. So this is quite helpful, because the cone will change depending on the position of the camera.
Okay, thank you.
Thank you.
Okay. There's time from some question if you want.
Hi. I was just wondering, when you're pre-processing your videos, I assume you're downsampling them somehow? You're not doing every single frame?
The videos are quite short, about 15 seconds. So we have usually 500 frames. So we usually don't downsample it. Sometimes we try to take smaller videos centered around the event, but it didn't change that much, actually.
Thank you very much.
Thank you.
Are you planning to use some other sensors like LiDAR systems, which give you the 3D view?
Currently not. There is one of the possible evolutions of the system. It might be quite a lot useful, actually, but currently we are not planning on adding that, because it would add a cost to the customer to add other sensors to their cars, to their vehicle.
Thanks.
Thanks.
Okay. If there is another question? No? Okay. Thank you, Andrea.
Thank you.